Hello and welcome to my expanded presentation on the feasibility of an OAI mask aligner at Rio Salado College. My name is Wesley McIver. Let us begin. Today I'm going to provide you an in-depth look at my research if perhaps you have not had a chance to view the poster. This study was initiated with one goal in mind, to be able to incorporate the mask aligner into a curriculum. Rio Salado purchased the mask aligner back in 2018 and has not been set up since. With the support of the NSF, who funded a research trip to the University of New Mexico Fab, I was able to determine what is required to support a mask aligner and to be able to use one in operation. The research is being conducted to support Rio Salado's goal of having a small fab that can produce patterned wafers. Currently, Rio Salado only has an electron microscope in operation, and they hope to be able to bring the mask aligner alongside it. Before I get too far into this, I would like to explain what a mask aligner is. It is a device that exposes UV light through some pattern onto a wafer that has been coated with a photoresistive material. This device is necessary in semiconductor processing for being able to make fine lines and spaces onto a wafer surface. The wafer is held against a mask, a device that allows or disallows light to pass through, with a vacuum, where it is then shown to the wafer and hardens a photosensitive chemical. The reason I was chosen to conduct this research is because of a background in capital equipment installation for Intel and Micron, as well as electronics work for the US military. I find the most enjoyment when I'm given an open-ended project like this, so I was eager to get started. The immediate hurdles to this research were known right away. They are the fact that the mask aligner will not be operated in any type of cleanroom, and the fact that this equipment requires N2 to operate, which is a health risk in the space it currently resides, which is a room about the size of a walk-in closet. I'm aware that most processes in the semiconductor industry require nitrogen to operate, and that hazard posed by this gas must not be taken lightly. At this point in the research, I was advising that the operation of this equipment should be in a larger room with the proper ventilation, as this would prevent nitrogen exposure to students and staff. The first step to this research was to see the equipment, which happened on June 9th, 2021. It had not been completely unboxed, and it still had packing materials present. In a very short period, I was able to determine that the mask aligner would still operate, though I had no knowledge of how it would do so. It is made up of standalone pieces meant for a desktop space. The illumination controller and the alignment base make up its parts. The illumination controller is responsible for powering the UV light source and monitoring intensity and voltage, and the base is responsible for maneuvering the wafer under the lamp, which contains the vacuum and microscope elements. The mercury lamp had not yet been installed, and it was clear to me that nobody else at Rio felt confident enough to set up this equipment. The documents immediately accessible were the operational manual, but this referenced two other documents that could not be located. For the missing documents, I had to reach out to Sam Pittman at OAI. After verifying Rio was the owner of this equipment, he produced the UV light source and constant intensity controller manuals. At this point, it was determined that the necessary facilities are as follows: two 120 volt 60 Hz AC power outlets, 25 inches of mercury vacuum source, 20 psi of nitrogen, 60 psi of compressed air. The gas and vacuum lines are made up of 1/4 inch quick disconnect fittings. During the UNM research trip, I was able to learn a lot about the requirements of a mask aligner in operation. Under guidance from Dr. Plyle, we used the mask aligner several times as we made art wafers and wheatstone bridges. With guidance from Mark Hoffhines, I gained immense knowledge about this equipment, as well as the facility needs to support a mask aligner. Some of these needs included a mercury spill cleaning kit for in the event of a mercury bulb break, as well as a UV intensity meter, so that we can ensure a consistent exposure across the wafer surface. Since exposure is such a critical part of a wafer fab, it would be unwise to operate this equipment without being aware that certain wafer positions could have a 5 to 10% variance in milliwatts per centimeter squared. Additional facility needs include fluorescent bulb filters to prevent premature exposure of a photoresist, as this can ruin a process before it has even begun. Additionally, PPE will need to be purchased to protect against UV rays, which include goggles and gloves. Students should be trained and aware of all potential risks to their health from UV sources. All of the additional materials and equipment should total less than $1,000, but will depend on the size of the room to be outfitted. I was able to adapt a form that UNM uses for the calibration of the UV light source. This is necessary as often a UV light source will need its voltage increased through its life cycle to maintain the same intensity. This form should accompany the UV intensity meter, as it can be used to ensure a uniform exposure intensity and to allow as left values to be recorded when changes are made to the UV directional lenses. The findings of this research concluded that there are no need for N2 to operate the mask aligner and that compressed dry air can be substituted in this instance. This data was presented in the UV light source documents and confirmed by Sam Pittman during some discussion. Again, this was one of the largest hurdles and risks to completing this research, as the nitrogen in the confined space where the mask liner resides is an asphyxiation risk. Without N2 in the mask aligner system, there is some risk to the mercury lamp as N2 is used to keep the glass enclosure cool. This can be mitigated with temperature controls in the room, as well as limiting the usage duration. If the lamp is used for approximately 6 hours in one day, a handful of times a year, this can minimize the lamp risk. When we substitute the clean dry air, we can add 26 psi versus the 20 required to achieve similar cooling characteristics. Expanding briefly on this, the nitrogen contained in air consists of roughly 78%, and increasing the air pressure will provide the same amount of nitrogen to cool the mercury lamp, and our change of gas should not have any measurable difference. The specific volume of nitrogen in 26 pounds of air is 20.28 pounds. I was able to produce a shopping list of under $1,000 for everything necessary to facilitate the mask aligner, and all of this was easily purchased online or locally. An air compressor for less than $100, an inline moisture filter for roughly $100, as well as a lab-grade vacuum system for $680 were included in this list. In our use case, we will use clean dry air instead of nitrogen for the reactor chamber cooling, and our compressor can provide for all of the demand related to the mask aligner. Quick note about the vacuum pump is that the vacuum return must be set up to go to a facility return, as this pump will be used to mitigate mercury vapors in the event of a lamp break. With all of the required items identified, Salado will need to train a staff member on operation and sustainment of an OAI mask aligner to ensure it can be operational for all classic activities. Training for response to a lamp break will need to be developed and the responsible parties identified in the event of a cleanup. It will also be necessary to determine if the UV lamp will remain on, as it can only sustain so many power up and down cycles as temperature variation risks a lamp break. With all of these items now identified, Salado staff can make an informed decision about the future operation of a wafer processing fab. Although the mask aligner can become operational, it is meaningless without other critical equipment. A stretch goal given to me by Dr. Vaughn was to determine a possible curriculum inclusion for this equipment. I am glad to be able to reach this stretch goal, though the answer is not favorable. Salado does not have the capacity to process wafers, which would prevent students from having access to this equipment in a meaningful way. The capacity to produce patterned wafers is met by the need for an HMDS exposure station, as well as spin stations, hot plates, and fume hoods. Additional requirements are the chemistry stations for a development bench with fume hoods, along with the necessary wash and rinse stations. Salado College would need to establish a chemistry lab with the necessary equipment before they could support any type of wafer processing. Future research would investigate the requirement for chemistries and equipment to be brought to Salado and to determine the cost of a complete chemistry lab with the space available for semiconductor processing equipment. I would like to thank a few people with this time. First off, the staff at UNM, along with Dr. Plyle and Matt H. for sharing lots of knowledge with me. Thanks to the NSF for funding that allowed me to spend a week at UNM. Thank you, Dr. Vaughn, for the challenge and this opportunity. Thank you, Professor Hyder, for keeping me on track and helping me overcome challenges related to this research, as well as the staff at OAI for their quick response.